All right. Okay, so I guess the next thing that I want to mention is what would be some potential problems if we start using virtual machine, right? So here is how virtual machine really works. So you have the host. I guess I will put client on the left side to make it easier to see here. Client and the host, right? So this is the virtual machine, right? And the host is basically the host machine. And when you run a virtual machine, what actually happens is you have a program like int star I, right, running there. And you need to do the host and the client has its own OS, right? For example, the client can be running Ubuntu while the host running Windows, right? So you have, when you want to do address translation, what really happens is you have your virtual address, right? And then you go to the page walk, which means that you go to level 1, page table level 2, and then the page table level 3, and then the page table level 4. Then you have the physical address, which try to access the data somewhere in the host DRAM, right? This is a physical machine. The host is basically your physical machine. To make it a little bit more clear, I'll use the blue text for the host, right? Because if you think about it, virtual address, when you go to page table, level 1, 2, 3, and 4, right? Page table level 1, page table level 2, page table level 3, page table level 4. These are virtual address on the host. These are host virtual address. So this guy is actually the host virtual address, which means that it has to go to level 1, level 2, level 3, level 4, right? To get to the actual page table level 1, right? So again, let me redraw this for clarity, right? So basically, each time you have to go to the page walk from the client, right? Means that you have to go to host level 1, host level 2, host page table level 3, host page table level 4, before you go to the actual page table inside the client virtual machine, which means that this part also do the same thing. You have to go to level 1, you have to go to level 2, you have to go to level 3, then level 4, before you go to the page table. This also means the same thing. You have to go to level 1, followed by level 2, followed by level 3, followed by level 4, before you can get to the page table content, right? So this is page table level 2, page table level 3. Before then you go to level 1, level 2, level 3, then level 4, before you can go to the page table level 4. After you have the physical address, this is the host VA, host virtual address. So you go to level 1. So you go to basically level 1, 2, 3, and 4. In order to get the physical address, so you basically have to go to DRAM 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 DRAM access. So that's what happens when you have a virtual machine. Your virtual address inside the VM have to go to 24 level of DRAM access to get to the physical address inside the host DRAM, the actual physical DRAM from your host. So this is called nested paging, right? It's something you have to do, and there's quite a few techniques that you can do to address the problem. The other thing that I want to talk about is the virtual machine in the world of big data, right? When you have things like a huge graph or huge data set inside ML training or ML inference, right? You can use huge page for that, right? Because it does benefit from larger TLB reach. But again, as I said, right, the key problem, fragmentation, bloat, and page replacement policy because of the fidelity loss, which is the same example I showed earlier, right? With the Willis Tower and have to clean the side of the window, right? If I use large page and the window pane is dirty, I cannot tell which one is dirty. So I need to clean the whole side, right? Which is not particularly efficient, right? So we basically look deeper into the problem and we found that the problem is in the metadata bits. It's allowed the hardware to tag the information about the page, right? Whether I have access to the page, whether I have that page present, or whether someone modified the page and the page becomes dirty. And that's done in the level 2, the 2 megabyte page table entry, which is the one before the last level. And that's in the metadata bits here. And the OS use this information to manage things like replacement policy or the mapping between fast and slow memory. These days you can have a technology where you have fast memory and slow memory as well, so you can use that to track the pages, right? The problem is the metadata information is coupled to the page size. So when you increase the page size to 2 megabytes, the fidelity information reduces as the page size increases, and the OS has no way to tell what the property of the small page is inside this huge page. And the issue is we profile, right, multiple applications on the x-axis, as you can see here, and measure hotness. Hotness is measured as how often do I actually access parts of the page. Now you look at 2 megabyte range, and as you can see, there's only a fraction of my 2 megabyte range that's actually hot, right? That actually get frequently accessed. But the thing is, if you use 2 megabyte metadata information, you track every single one of these pages as hot. So everything looks hot here, right? Which means that if I need to kick something out of the memory to the disk, I cannot tell anymore. I just ended up randomly kicking things, right? So we propose a solution called PRISMs, which basically decouple this metadata granularity from the page size by allowing finer grain and variable metadata granularity, and it's also applicable to both CPU and GPU. We'll talk about GPU translation when we start talking about GPU, which comes in a few weeks. I'll talk and introduce some of my work that looks into how to do the translation for the GPU. But PRISM has 2 main components, the page table extension and the TLB extension to make everything work. And here's the overview, right? So this is basically your de facto how you do translation in a 4-level page table. But when you have level 2 index, this is what you do. So you go and append your page table with another copy, but now you have the metadata registry, which is 64 bits. The left side store, the left half store the access bit. This maintain the information of whether I access the page or not. The right side, I store the dirty bits, which maintain the information on this smaller granularity on whether I modify the page or not. And when you have to go through this particular level, then you jump to the correct MRE position to figure out whether you need to look at the metadata bits or not, and what is the granularity of the access and the dirty bit, because we want to be able to track different granularity from 16 kilobytes to 64 to 128 to 512, for example, right? And then you go to index level 1 as usual. And the encoding for the MRE entry, again, 3 bits in total, which means that we have 8 different options for the granularity. When the encoding is 000, we use 1 bit granularity. Otherwise, we go basically 2 times the amount from there. So MRE of 001 is 2 bits, 010 is 4 bits for the MRE granularity, depending on how fine grain of the small page that you want to track. Then you also have to change the TLB granularity as well, because now you have the MRE entry attached to them. So you need to be TLB basically need to be aware of the corresponding MRE entry, so that when you have a TLB hit, you can update the access and dirty bits and set them accordingly, so that when you have the TLB miss, you kick something out, you bring in the new entry, and the page walk cache would extend the page table walker to be aware of this corresponding MRE entry inside the TLB. And we provide the interface in software through the command mmd config, where you can specify the address and the length and then the bits for your metadata granularity. And we extend our GPU virtual address translation work so that we can model the GPU workload and run 15 different GPU applications, ranging from things like convolution to things like matrix multiply on the GPU that model GTX 750 Ti. And we found that from the y-axis here, normalized performance across all these workloads. On average, our design PRISMs is able to prevent the slowdown seen by the 2 megabyte baseline for the workload that see the slowdown. For example, this guy, and this guy. Once you can actually use the finer granularity, ray tracing doesn't get the benefit. So once you have a finer granularity, on average, we are able to recover the performance difference depending on how we configure that, which can be configured through the software. So we found that it's actually effective when application demand fine-grained metadata information. So we can then look into how to manage this under different conditions. And this is a work in PAC 2020, which is one of the top conference in parallel architecture and compilation techniques. This is a work done by me and my collaborators from UT Austin VMware Research. And that's when we talk about virtual machine for big data applications, including VM in the cloud, right? So these are VM in the cloud. And then we also look into VM in other type of processor like a GPU. So we're not going to talk about these in detail. I just want to motivate that also works on how to deploy virtual memory for different entity and different hardware that you can see nowadays, right? So I want to kind of wrap up the talk and this lecture today by saying, hey, you also need memory protection for your GPU to allow multiple GPU application like machine learning to run concurrently in the cloud. So basically, you want to share the GPU in the cloud. This is still a big topic of research because you need a better resource utilization. The current solution is not good enough to utilize every single thing you have on the GPU. So you might need fine-grained sharing. And this allows fine-grained, basically requirement is you want virtual memory apply to have fine-grained sharing in the cloud. So once we learn about how the GPU works, then I'll talk about some of the works that I've done in this series of how do you have fine-grained sharing in the cloud on the GPU side that we have published so far, and how we design the virtual memory on the GPU. All right. So that's it for the lecture today. Any questions?